Omicron Ceti, commonly referred to as Mira, is a red giant star. It is also a red giant variable star. This is a Chandra image, an X-ray image. It was seen for several years that Omicron Ceti had a really odd little bump on one side of it. And this Chandra image shows that that little bump is actually, not only is Mira a Mira variable star pulsating, it also has a white dwarf companion. And there is mass transfer taking place at a contact point between the two. This is an artist illustration of Mira, Omicron Ceti, and its white dwarf companion. And here is a Galix image, ultraviolet image of Mira at the top, an optical image below, and unless you see it in ultraviolet, you would have no idea that Mira is plowing through space-time at a pretty good rate, sloughing off material. Every time it pulsates, it leaves material behind, and you can see that material spread out through space-time as it plows along, and you can actually see the bow shock of material being compressed and bunched up in front of the star in its direction of motion. SS Cygni is, we've had this one before, quite a while ago, and this is a dwarf nova system. It is an extremely bright one. It is a white dwarf that has a low mass main sequence companion star, or red dwarf. They are very close in proximity as they orbit each other. And there is the difference between a dwarf nova and other types of nova is that the instability isn't taking place on the surface of the white dwarf, it's taking place in the accretion disk around it. The material in the accretion disk seems to reach some kind of critical mass, and all of a sudden it dumps a bunch of material onto the surface of the white dwarf and results in what's called an outburst or a flare or a nova. And it happens, it keeps doing that periodically, fairly periodically, but again, it's caused by the instability of the material in the disk, and this is what a light curve, if you plot it over time. It's also sort of a recurrent nova, and it's pretty periodic in its outbursts, so there's some instability in that accretion disk that just keeps happening over and over and over. Actually, this particular variable star has been observed more than 100 years, so they have a really long light curve for SS Cygni. Sirius A and B. Sirius A, of course, is the apparent brightest star in the northern hemisphere when Canis Major is in the sky. However, it's pretty close. It's only 8 light years away. It's only a 2 solar mass star, so that's why it appears so bright to us, but it also has a white dwarf companion. This is what it looks like in an optical image of Sirius A, and you can see the little white dwarf companion down to the bottom to the left of Sirius A, and this is what it looks like in optical, because white dwarfs emit very little radiation in the optical part of the spectrum. This is a Chandra image. So if you look here, you will see the bright image is Sirius A, the primary star, and the little white dwarf companion you can barely see, but in the X-ray image, the bright one is the white dwarf companion, and the one that's dimmer that you don't see so much is the primary Sirius A star, because that one doesn't emit anywhere near as many X-rays as the white dwarf does. The AM CVn systems are very rare cataclysmic systems. They have 2 compact objects in a binary system. They usually have less than 1 hour orbits. They're orbiting very fast, very rapidly, and they are thought to be a source of gravitational waves as the orbits decay, that energy has to be transferred somewhere else. They have finally recently detected gravitational waves from the merge of two black holes. If you go on YouTube, you can actually hear the sound of two black holes merging. We haven't caught anything yet, I do not believe, from two little white dwarfs. A lot less mass involved with that one. However, these should definitely be producing gravitational waves. Also, these two objects here, J075141 and J174140, are both binary systems. They are rapidly approaching the CVn category of cataclysmic binary stars, and they are either, when they come together, there's more than one possibility as these stars merge. When they merge and come together, they can, number one, maybe it will just, there's one white dwarf accreting material off in another white dwarf. If you have that's very seldom, you're going to have two white dwarfs that have the exact same mass. So the more massive, more compact in diameter, smaller in diameter, but more massive white dwarf can accrete material off the surface of the less massive white dwarf, and it actually can be when they come together, if their total combined mass doesn't exceed Chandrasekhar's limit in that region of mass, then it can coalesce into a larger white dwarf. So larger in mass, but smaller and more compact in size. Or if it, and here we have those where those little neutron stars come in, if they merge in such a way that the total combined mass is between 1.4 and 2.4 solar masses, either two things can happen, and one of them is that they can coalesce into a neutron star. And then with a neutron star, of course, the electrons, it is so compact that the electrons get shoved inside the nuclei of the atoms where they combine with the protons and become neutrons. So now we have neutron degeneracy pressure, again, degenerate matter, that is holding gravity at bay from collapsing the object anymore. But it can be a more violent thing than that. They can come together in such a way that it produces a type 1a supernova event that destroys the white dwarf. And there is actually a scenario where they can come together and it can sort of damage the white dwarf, but not cause it to destruct or coalesce into something else. And then you would have an event that is only 1/10 as bright as a type 1a supernova event. So they would call that event a 0.1a type supernova event because it's 1/10 as bright as the type 1a.